Fine. So now that we know that data cleaning is essential. Okay. So there are of course data cleaning is essential, and you will have missing values in your data set. Of course, you will have missing values in your data set. Okay. So there will be. So today we'll discuss something about known as complete case analysis. What is complete case analysis? Okay. So, to dive that, one of the motivation to start with complete case analysis is regarding missing data. Okay. So, of course, you will have missing data. So, if you have missing data, what you need to do? So, suppose you have missing values. You have missing values, and those missing set of values, you can either remove them. You can either remove them. That means you can remove entire row or column. Okay. As we discussed, like if something is missing, you can remove that entire row or column of the data set. Or what you can do next is fill them, fill the missing values, fill them. Okay. Another way or scientific way to name them is known as impute or imputation. So you impute the missing values. So this is known as something known as imputation. Okay. Data imputation. Fine. So if you have to fill the missing values, the term is known as imputation. So you impute. Fine. Now let us consider a tiny rough data set. So you can see suppose this is our data set, okay, which has lot of columns like that and many rows. Okay. Now suppose the data in most of the columns are already filled, but suppose this entry is not filled. This entry is not filled. Now suppose to fill this entry, now you can either remove them. You can remove this entire row. That is the first option, A. Or you can impute them. That is known as data imputation. Okay. Now suppose while considering the method of imputation, to fill that entry, you are using only that particular column. Only one column if you are using. Okay, maybe what you can do, maybe take the mean of the remaining entries in the column. Okay, all the entries in the column, take the mean and fill it up. Or take the mode of those and fill it up. Okay. Till now, I have not mentioned to you whether it is a categorical variable or a numerical variable. Okay. If it is a numerical variable, you can fill it with mean, or you can fill it with median. Okay. Or you can fill it with mode. In categorical variable, more likely you cannot apply mean and median, so you can apply mode. Okay, to it most likely. So if you are filling that particular missing value based on that single column, mind my word, single column, then it is known as something known as univariate. You focus on only one row or column. Okay, fine. Now suppose in order to fill this missing value, you are taking help of these values, this column, this row, okay, this row, multiple rows and multiple columns. This column also you are taking in order to fill only this value. So you are using multiple rows and multiple columns to impute or fill the missing value. Okay, not single column, rather multiple rows and multiple columns. Then it is something known as multivariate. That means you focus on multiple rows and columns to impute. Okay. So regarding these are of two types: univariate imputation and multivariate imputation. Univariate, now you know what is univariate imputation and you know what is now multivariate imputation, right? Now, in order to perform in this class, we will mainly focus on the univariate imputation. Okay. Most likely you will learn about the multivariate imputation in your next semester in predictive, most likely. Okay. So in your univariate, you will mainly focus on two different variables, that is numerical, categorical. Okay. So yeah, if you have numerical variables, you can impute the missing value by using mean or median filling. Okay, you can fill the missing value by mean and median, or you can randomly fill. I mean, you can assign any random value to the missing row or missing entry. To the missing entry, you can randomly allot any value, or you can assign a mean of that row or mean of that column or median of the row or median of that column. Okay, in that missing value. Fine. Another is something known as end of distribution method. Okay, which we won't be covering much in this class, but just for your sake to know. It is known as end of distribution. Okay. For categorical variable, there are two ways to, if you have a missing entry for a categorical variable, what can you do? You can calculate the mode of that row or column so that you will know what is the maximum occurrence of that categorical variable, and that you can replace it with mode. Replace with the mode. Okay, with mode value. Okay, fine. Or else you can just write there in your missing value as missing. That's it. In letters, you can type missing. That's it. That's another way. Okay. So these are the two ways you can deal with categorical variable. If categorical variable is missing, you can replace with the mode, which is most likely, like we saw in the previous example in the marital status. If you have the marital status column, we saw there are 4 entries with single, 3 entries with married, 2 with that we are not covering in this. That you can explore. You can explore. I mean, this is something more detailed. This is something more detailed which we want is outside of the scope. Okay, there are something more also which needs a bit of predictive analytics. Will not see, but end of distribution you can always look into yourself for you to explore. Okay. Fine. So this is one. Now coming to multivariate. Now that we know about, now in this lecture we will focus only on univariate. Okay, in this course actually we will focus on univariate here only. Regarding multivariate, we won't be focusing in this semester. Multivariate is most likely to come in the next semester in predictive. Okay, fine. Okay, in multivariate, but I will tell you some methods here just so that you can Google them and watch or view any materials on the web. Something known as KNN, imputer class. Okay. So if you have multivariate data sets, multivariate possibilities, you can use KNN imputer class. You can use KNN imputer class, and there is also another imputer known as iterative imputer. Most popularly, it is referred to as mice. Okay. Most popular, yeah, sorry. Yeah, something is weird. Okay, fine. So imputer mice, okay. So you will know that, yeah, you can use something known as simple imputer class, which is available in Python. Simple imputer class, which is available in Python, and you can use scikit-learn for that. But this is also a bit outside scope, and we will not be seeing that here. Okay, fine. So when we are removing the missing values, it is known as complete case analysis. Okay. So when we are missing, when we are removing the missing values, okay, it is referred to as CCA, that is complete case analysis. Okay. We will see this is a method. Okay, we have to remove that particular row, that entry, okay, that column, that is known as complete case analysis. Now the question is when to apply complete case analysis and when not to apply complete case analysis. Okay. So you will apply complete case analysis. We apply or perform CCA, that is complete case analysis, only when the data set or the data in data set, the data or the entries in data set is missing completely at random. Okay, missing completely at random. Sorry, I'm facing this issue a bit. Okay, okay. So missing completely at random. Okay. What do you mean by a data set to be called as missing completely at random? That's one of the questions. Okay. Suppose you have a data set. Suppose you have a data set like this. It has many rows and many columns. Okay. And you will see that let me mark with red, those are missing. Okay. This is one of the entry which is missing. This is another entry which is missing. Another entry. Okay. But this has a pattern to it. This is a pattern to it, isn't it? Like three consecutive entries are missing. So therefore, it has a pattern. We cannot say that it is missing completely at random. So you cannot apply CCA to this case. If your data is not missing completely at random, when you tell data is not missing completely at random, when you see a pattern in the missing values, if you see a pattern in your missing values, you say it is not missing at random. Okay. When can you say it is missing at random? Suppose, for example, like this is missing, this is missing, maybe somewhere here it is missing. Yes, you can say that yes, they are missing completely at random. Okay, they don't have a pattern to it. But when you see that yes, you can say clearly that this is not missing completely at random. This data set is not missing completely at random. Okay, why? Because you see 3 rows and 2 columns in a pattern, they are missing the values. Okay, so therefore, when we only perform complete case analysis only when the missing data is missing completely at random. Okay, if your data set is not missing completely at random, it is not a good method to use complete case analysis, that is removing the missing entry. Okay, fine. So this is missing completely at random, that is known as MCAR. So now you know the abbreviation. CCA means complete case analysis. MCAR means missing completely at random. Okay, fine. One of the most important logic we are making here in this, which is not that clear to a wide audience, is you apply CCA, okay, to data which is missing completely at random, first case. And second case is, if you perform CCA, so data will be changed. If you perform CCA means you're removing that data entry, right? You're removing that entire row. Okay. Now, if you remove that entire row, the column, that particular column or the particular row is not there in your data set. Okay. So the data set has changed. Okay. Now, there are two data sets, before, after. So before applying CCA, and after applying CCA, you can agree to this method of CCA only when one condition is met, that we will describe here. Okay. So what you do before applying complete case analysis, you make a distribution of the data set. That means in this plot, you will tell how many of them are males, how many of them are females, and how many of them are lying under the age of less than 25 or greater than 30, like that. And you make a distribution, right? Some kind of distribution here. Okay. Now, when you remove that particular data set, when you remove the particular entry of a data set, after applying CCA, what you will see is, if you plot the distribution again, then the distribution should be similar. After applying CCA, if you are getting similar kind of distribution, not exactly the same, but similar. Okay. If you get a similar kind of, this is distribution A, this is distribution B, then distribution A should be similar to distribution B. If it is not similar, then performing CCA is not a good idea. Okay, I hope that is quite clear, a bit clear. I hope you got the logic that if you have a data set, you distribute the data set, make a distribution of the data set, plot it, you will have a distribution. Okay. Now you apply CCA to it, remove the missing rows, remove the missing columns. Okay. And then again plot the distribution of the new data set after applying CCA. After applying CCA, again you will have a new data set with less size, right? Because you have removed the rows. Okay, you will have data set of less size. Now, if you make a distribution of that, it should be quite similar to the previous original data set distribution. If the distribution is similar in both of the cases, then yes, then it is a good idea to apply CCA. That means if the distribution is same even after applying CCA, it means that a lot of features are not getting destroyed. Lot of features you are not losing in your dataset. Okay, so the distribution should be the same. If the distribution is not the same, then applying CCA doesn't make any sense. Okay, that we will see with a particular example in Python. I will show you that the two distributions in a particular dataset, we'll import it from GitHub, and you will see that they are matching. The distribution after applying CCA, before applying CCA is kind of matching. Okay, so therefore applying CCA is good, like in those examples. So this is the logic. Okay, so the distribution before, so what's the idea? So the idea is CCA would be successful if distribution of the data set, okay, distribution of the data set before applying CCA is similar, this is a similar option, similar symbol, so is similar to the distribution of data set after applying CCA. Okay, that we will see. Okay, fine. So these are some of the cases. And to apply CCA, that means what you have to do? In order to perform CCA, you have to remove that row. You have to remove that entry. In order to remove that entry, what you can apply? There is a particular command in Python that is drop NA. You can call drop NA command here to remove that particular entry or row in which you want to apply CCA. Okay. Now that we know what is CCA, that is complete case analysis, there would be some advantages and some disadvantages of that method. Okay. Now, what are the advantages of CCA? What are the advantages of CCA? Any ideas? So one good advantage of CCA is it preserves dataset distribution. Okay, that is before applying CCA and after applying CCA, the dataset distribution is quite similar. Okay, that you normally don't see in other methods. If you replace it with a mean or a median, then most likely the distribution might change. That we will see. Most likely, if your data set has an outlier, then if you impute it with mean, then the distribution will change because it goes towards the value which is larger. Okay, so if you perform mean median imputation, then this distribution of dataset preservation might not be there. Okay, if you are doing mean median imputation, this dataset preservation might not be there. It can be there. Most of the cases, if your data is skewed, it won't be there. Because if your dataset is skewed and you apply the distribution of the dataset, it will be left skewed or right skewed. That we will see now. But after removing that skewed part, then the dataset will be almost normally distributed. So the distribution will be a bit different. Okay. So therefore, one advantage of CCA is the distribution will be the same before and after applying CCA mostly. That's one of the advantages. Okay, here we are discussing the advantages. Any other advantages you can think of? Okay. Any disadvantages it can have? Any disadvantages CCA can have? Hmm? Yes. Yes. Actually, if your data set has lot of missing values, suppose your data set has lot of missing values, then what CCA suggests? Remove all of them. Remove all of them. Now, if you remove many missing, if your data set has many missing values, many, see the word many, okay, many missing values, and you apply CCA, what does it happen? You will remove all the missing values. Then your data set will be left with very less entries. Okay. So with less entry data set, how can you perform analysis? How can you perform analysis? Right? Any other disadvantages? That's one of the most like very big disadvantage of CCA. This is the reason why most of the times you don't perform it. You don't perform it because of this reason. Okay. If we have a condition actually that I will tell you. So the catchy points or the what I can say, some of the limitations of CCA is you use CCA only if data is MCAR, that is missing completely at random. If it is not missing completely at random, you cannot apply CCA at all. That's the catch. Okay. And second point is we don't apply we don't apply CCA if more than 5% of your data in your data set is missing. I mean, if your data set has lot of missing values, what do you mean by a lot? We have to characterize what do you mean by a lot. So the lot means greater than 5%. If your data set has more than 5% missing values, then it is not wise enough to apply CCA. That's the catch. So whenever we will see that I will show you the Python commands or the programs. So where you can see we test for a particular column before applying CCA whether the number of null values is less than 5% or not. If the number of null values is less than 5%, then yes, it's a green flag to apply CCA. If your null values is more than 5%, then it is a no-no to apply CCA. Okay. So that's how, I mean, it's a method in its own aspect. So now you know what is CCA. Now you know when to apply CCA. Okay. I hope that is a bit clear. Okay. So now we know when to apply CCA, what is CCA, what is MCAR, what is missing completely at random. Okay. So those kind of aspects. And I hope you understood the logic behind it. That's what is more important. Okay. The logic behind is more important. Okay. That's the same thing. Whatever we have taught in theory like this, we will see that in running in codes. Okay. We'll see that the distribution is coming similar. So what we will do to show this is we will take a very nice data set. We'll take a very nice data set which is already much cleaned. We'll take a nice data set which is already much cleaned and which has very few missing values. Okay, so it satisfies less than 5% case and you can apply CCA. We will apply CCA and I will show you the distribution before applying CCA and after applying CCA, and we will see the distribution merge with each other. Both the distribution merge with each other. Okay, if the distribution before applying CCA and after applying CCA merge with each other, what does it mean? What does it mean? Distribution is similar and the CCA is successful. Like applying CCA is successful. If the distribution did not merge with each other before and after applying CCA, they differ by a large amount, then it is not good. Then it says that yes, some aspect is there which the distribution changes after applying CCA. In general, distribution of the dataset should be preserved after applying any kind of a method. Then only the original dataset features will be there. If your dataset distribution has changed, then the features of the original dataset is changed, which is not good, right? Do you want the features of your original dataset to change? No, that's not required. That's not desirable. Okay, fine. So we'll see. Maybe we can see that in Python. Maybe where it is it this one? This one? I don't know. I will get error. I think it is disconnected. I think here we apply. I think so. Yes. So you see, this is the URL. Okay. So I am getting this data set from this GitHub repository. Okay, and it's a CSV file, Glassdoor CSV file regarding, I think, jobs of data scientist role. Okay, so you can see the job title, the salary, lower estimate, higher estimate, and what's the job description, and the salary rating. Okay, sorry, the rating of the job they are in, and which is the location outside of India it is there. Fine. So what we are trying to do here, I'm reading that CSV file. You can see pd.read CSV. It's your old command. Okay, and this is how you read this. Like you apply the URL command. That's it. Okay, you paste the URL. What I did is I went to the GitHub, got this data set from this username. Okay, and I pasted the location here. Okay, so from that GitHub lively, it is catching those data files. Fine. And then I'm printing the first 5 rows using df.head. Fine, that's okay. Here I'm calculating in this command, you can see below okay, let us see first a bit more. You see how many columns are there? What kind of columns are there? So you can see job title is there, salary estimate is there, upper and lower job description, rating, company name, location, city, state, size, founded, etc., private or public funded, those things are there. Now what we are doing is we are trying to find a percentage of missing values in each of the columns. We are trying to find percentage of missing values in each of the columns in your dataset. So for that, what we are doing is df.isNull command and the mean times 100. So it will give you a percentage. Okay. So you are checking how many entries in my column is isNull command. Okay, through isNull command, and I am taking the mean multiplying with 100 to give me a percentage. Okay. So you can see that yes, job title, you can see job title has 1.9% of data missing. Job title has 1.9% of your data missing. Now, what is a job title? Job title is the column here. It's a categorical column here. Okay. Job title has, here it is not able to see, but you can play around with this. I will share this with you today. One of your task is to find at which row your data set is missing. In which row entry the first column data is missing using isNull command. Okay, here I have used isNull command to find the percentage. Okay, here I have used isNull command to find the percentage. Of course, see, there are multiple aspects to reach to this conclusion. As I told, the assignment I gave to you in the class, what is the assignment I gave to you before? What question? That one tell. Huh. What to do? No, I gave you regarding LOC and ILOC, I think, no? Yes, LOC and ILOC, that assignment, right? Yes. So as we know that we extracted the first row. We extracted the first row in the class by using head and tail commands. Okay, like he said. And instead of that, you can even use n is equal to 1 kind of thing inside the bracket and get the first row. So there are multiple aspects you can achieve this. There is no hard and fast rule which I am showing only can be achieved. Maybe this is even confusing to some people. This one-liner code which I am writing here dot isNull dot mean. So it has something more to it. I suggest try to understand this. Okay. Anyway, you can even do like LOC command if you are interested. Okay. So the aspect, the main motivation to do this is to check my theoretical criteria that whether the data sets in the columns are missing, those who are missing are less than 5% or not. If it is less than 5%, I told you that we can apply CCA. Okay. Now you can see the data sets are mostly yes. I mean, I think 1.93, it's all same in all the columns. I feel that one of the row might be missing or equal number of rows are missing. Okay. And each column entry are missing at the same time. So you are getting the same percentage. Okay. I mean, like if you are missing one row you are missing and all the columns are missing, then the percentage will be the same. Then the percentage will be the same, right? Fine. So, hmm? Yeah, good. Yeah, I missed it. Yes. Yeah, I think that is the reason I took this example and I missed it. Okay, anyway. So it should be like this. Like you can see this more than 5% is missing somewhere here. More than 5% is missing here. Fine. Now that you know, there are some columns which has more than 5% and there are some columns which are less than 5%. Remaining columns, I think less than 5%, right? So what you can do, you need to select the columns which have less than 5% of missing data. You need to select columns which have less than 5% of missing data. Okay. You don't need to worry about the columns which have more than 5% of missing data because you know you cannot apply CCA to it. You cannot apply CCA to it, more than 5% of missing. So here I am doing this command which I suggest is no pressure to understand because the for loops will be new to many of you. Okay. So those who know about this is okay, but those who don't know about this is fine. Okay. So what I'm trying to do is I'm searching for the columns which has the missing value percentage in between 0 to 0.05. That's what I'm searching over here with a condition. If condition is there, if df call dot is null dot mean, this is how I'm getting the percentage. Okay. I could have multiplied by 100. Okay, but I have not multiplied by 100. So you will get in terms of decimal, like 0.05. If I would have multiplied by 100, like I did above, like here, you would get like something like 5 or something. But now you have to do within this 0 to 0.05. Okay, 5% is like 5 by 100, so it is 0.05. Okay, so no need to understand. Here we are just getting the columns with less than 5% of missing values. That's the idea. Okay, and you can see it is giving me. Is it giving me that column state? Is it giving me? Is it there? No, it is not there because less than 5% is already scanned. Okay, so you can see the state column is not visible here. Okay, so these are the columns which has less than 5% of missing data. Okay. Now what we need to do with those columns or rows? We should apply CCA. What does applying CCA mean? Remove it. Applying CCA mean remove them. Okay, remove those rows and columns. So if you want to remove them, you can drop them. Okay, that is through drop NA command. You can use drop NA command to remove them or to drop them, okay, from your data set. So you can see df.shape. Okay, this is the new data frame this is the new data frame which dropped the columns and rows. Okay, and that is the new df, new data frame. Now there are two data frames. Data frame before applying CCA, data frame after applying CCA. What is the name of the data frame after applying the CCA? That is drop NA. New DF. Okay, there is two DF now. DF and new DF. Okay. So of course, once you drop the columns and the rows, the size should differ. The shape and size should differ. So is it differing? Can you see that the original size, that is df.shape, has 672 rows and 15 columns? Okay. So sorry. 672 rows and 15 columns. When you apply new DF, that is when you dropped the rows and the columns entries, okay, you stayed with one column is eliminated. Okay, fine. You have that rest number of rows, that is 659. How many are removed? Around 22. No, says 12. 13 rows. Sure. So now we have two data sets. Now we have two data frames, that is DF and new DF. Now what I told in the theory part is, after applying CCA, it would be a success if both of your distributions, after applying DF and before applying DF, sorry, after applying CCA and before applying CCA would be same. Okay, so therefore we are doing a distribution here for both DF and new DF. Okay, so this will come more clearly in your data visualization part where we are doing this plot, but this is not needed for you. So don't worry that this is very tricky to understand what is density, what is color, what is alpha. So these are characteristic of a plot to make the plot more beautiful, nothing else. Okay, so you are telling that plot DF, plot the data frame distribution DF in red color and plot the new DF. Follow my cursor. Plot the new DF data frame distribution in green color. That's what it is. Okay. And alpha determines the opacity a bit. Alpha transparency. Okay. Alpha transparency. So that more detail will come in data visualization after 2 months of time. So no need to see this or get more deep to it. You can if you are interested, but more will be taught into you in the data visualization module. Okay. Fine. So you can see that before is red and after is green. Okay. And you cannot see the green. You cannot see the green. Why you cannot see the green? Because the green is, why we cannot see the green? Yes. So what I suggest is take this file. Today I will share this. Take this file and plot them separately. I have plotted both of them on the same plot. Okay, so you don't see the difference. But if you see the difference and the difference is bigger, I mean, you might have seen some green part here, some green parts here, then you know that the dataset distribution is very widely different. Therefore, applying CCA is not a good technique to you, to this dataset. Okay. So here both the red distribution and the green distribution, that means after CCA and before CCA are merging with each other. Okay. Fine. So that is it. I mean, yeah. Fine. So I hope that is something clear to you. Okay. So that this was the most important part I wanted you guys to listen to. Okay. Because many times we hear about cleaning data set like we do data cleaning, we do this, that, and remove the mean with this and that. But normally no one tells about this distribution comparison, which is likely to play a key role when you are actually doing a project. Okay, when you are actually doing a project before applying CCA or after applying CCA, you should actually match with the distributions. Okay, that is kind of more important. Okay. Now let us look into something else. Like go back to this. Okay. So fine. Shall I tell this or? Okay, maybe I want to put everything in one, so we can make a small box here. I'll just write so that you can have everything at one place. Okay. Now there are two aspects which remains to be discussed. That is what you do if your data is numerical. What you do if your data set is numerical data. Numerical data. So numerical data means numbers, decimals, integers, fractions, these kind of things. Okay. So what to do in that case? So if suppose your data set missing values is more than 5%, if the number of missing value, if the percentage of missing values is less than 5%, what you can do? You can apply CCA. If it is more than 5% and it is numerical, then yes, you can apply a numerical data set. So you can apply this technique, okay, which we are going to discuss to data set which has more than 5% of data missing. This is one of the advantages of this. This is one of the advantages. If your data is missing more than 5%, you can apply this numerical technique over here, keeping in mind that your data set actually has numerical values. I mean, if your data set has categorical values, there is a different method. But if your data set has numerical values or numerical entries, and your data has more than 5% of missing values, then you can apply this method. The method is something like you can replace or impute with mean and or median. Okay, you can impute with mean and median. So this is known as mean median imputation. Okay, this is known as mean or median imputation. Okay, but most likely one of the disadvantage of this method is like if you apply mean or median, okay, of the data set, replace that missing entry with your mean and median, most likely the distribution of the data set won't be the same. The distribution of the data set will differ. Okay, so that is one disadvantage. I mean, okay, so only the data set kind of remains with the same distribution only if you have CCA with MCAR, that is missing completely at random. Okay, and another disadvantage is outliers come into picture. So if you do numerical, mean median imputation, then most likely outliers can come into picture. Okay, like in your data set, if an outlier is there, okay, suppose an outlier is there and you're taking the mean, so the mean is slowly being pushed towards the outlier, right? And you will be filling that missing value with that big value towards the mean or towards the outlier, right? So that's how it is a bit tricky. Okay, so outliers can come into picture in those cases. If you're using mean median imputation, outliers can come into picture. That can be shown, but I have skipped that part because you can show it by a box plot. Okay, you can show it by a box plot. Those who know about it, or those who don't know about it, we can discuss in the module of data visualization. Actually, in box plot, you can see the distribution of the variables, and you can see that above certain part, that is interquartile range. If some values fall, it is known as an outlier. Okay, and you can easily visualize that when you do any mean median imputation after and before, you can see that after when you do the mean median imputation, the outliers started gathering into the picture in your visualization. That we will see. That we will see. So what is the disadvantages if you want to do the mean median imputation? Most likely outliers come into picture. Okay, that's one of the dangers. Now, how to deal with outliers? That we will discuss in this class also. What is an outlier and how to deal with outliers? Okay, fine. Another is arbitrary value imputation. I mean, we don't want the mean, median, mode, anything like we can arbitrarily fill any value, randomly allowed any value. Okay, randomly. That can be done, but again, what is the drawback? Yes, maybe you can fill with a very large value of a random value. Outliers can come into picture. Any other? Yes, exactly. The distribution will change for sure because randomly you are filling. So of course it won't see the mean. It won't take the help of nearby rows and columns. So therefore, definitely the distribution of your data set will change. That's not a good thing. Okay. Fine. So distribution changes, outliers started coming to picture. Then there will be a lot of issue with covariance and correlation also because you are dealing with numerical data. So since it is numerical data, you can always compute the correlation coefficient. You can always compute the covariance, right? So when you impute with mean and median, the correlation started changing before and after. So these are the problems you will face when you do mean median imputation. But in some ways, it has advantages. Because if you have a lot of data set missing, that is more than 5% of your data set missing, you can still apply this method. But it comes with a cost that your data set shape will change, distribution will change. Okay, so these are the things, and you already know about the categorical data set, right? You already know about the categorical data set. Like if you have categorical data, okay, then like we saw the marital status example, okay, what you can do, we saw the mode is single. The mode in that data set is single, right? So you can replace any missing data in that entry in that column by single. So you can apply mode in categorical variables. So for categorical variables, what if you do categorical data? What you do if this I told I think already? No, I told anyway. So we discussed various method of imputation, that is filling the missing data in numerical data, in categorical data, and also using CCA. Okay, and when to say your data is missing completely at random. Okay, so categorical data you can use mode, and also you can use just write in your data set missing. This is mostly followed. Okay, fine. So this is the idea. So now, now that we have seen this part, uh, let us see what is an outlier. Mhm. Okay, skewness. Okay, skewness. So what is skewness? Hmm? Any thoughts? How many of you have learned about skewness before? Skewness. Okay, skewness. So skewness is like a statistical measure that shows how data is spread out in a data set. Okay, how data is spread out in a data set. How can you measure that? What do you mean by spreading of data? That means, how can you say spreading? I mean, you will say a bike is going very fast. When you say bike is going very fast, you compare it with a well-known speed. And to that speed, when you compare, it is going fast. Okay. If you tell like very fast is very slow in solar system. Very fast is very slow in solar system. Solar systems like planets, galaxies are orbiting like fast, like maybe we don't know, thousands of kilometers per second, something like that. So quite unpredictable scenarios. But so therefore, when you say data is spread out, you compare it with mean. Okay, you compare it with mean. Like this is the mean, and from the mean, how the data sets are, the data values or data entries are moving out. So that is known as data spreading. Okay. Anyway, so we will see. So when you this is kind of a distribution. When you plot the data distribution, like in this class, maybe when you plot regarding some values, can you tell me a data distribution like normal distribution? Yeah, like usually a test, like if we conduct a test, if we conduct a test here in this class, not with this many members, like whole SODS, like SODS whole DUK, okay, and we conduct a similar test, okay, statistical or logical aptitude and those kind of things, okay, and we compare the marks. If it is a good test, you will follow this kind of distribution, like a normal distribution. Okay, why? This is the marks. This is the marks. The number of people, okay, so who get highest marks is kind of a medium, okay, and the number of people who got lower mark is higher, okay. Usually people like I mean students, if it is a hard test, you will see something like this. Like many people are scoring very but what is the x and y axis here? That should be the first question. Hmm? X shall mark should be in, you want number of students in y axis, right? Okay, now, and you want marks on x axis, okay. So this is regarding a test. So what does it tell? It tells that those who got higher marks, this is higher marks, are less students. There are less students who got higher marks here. And there are plenty of students who got medium kind of marks. Okay. Like something 70 above or 60 above, something like that. And there are very less students also who are making very poor marks also. Okay. So a class test or an exam should be, this is an ideal exam. It's an ideal exam. Like if you plot the marks and if it happens like this, then it is an ideal exam. Okay. But for me, for my subjects, usually what happens is something different. Okay. For what happens in my case? Okay. What do you think? What happens? Huh? This side or that side? Left side. So you are telling this one. Huh? That's right. Okay. This one. You are telling this. That means what you are telling? You are telling no, that won't happen. Maybe it will happen something in a different way. Okay. So what happens in my case is a lot of students who get more marks is in the more is usually the maximum. There are maximum students who get higher marks in my subjects, and many people ask like why this is the case. We don't even. So if it happens like this, if it is happened like this, you can see it has a skewed distribution towards the left. So it is kind of left skewed. Okay. And if you have something like this, like number of students here and the marks are here, and you have something like this. Okay. So this is like kind of right skewed. So you'll see this. Okay, you'll see this. Now, there is something known as a, it tells us if data points are skewed to the left, that is a negative skew, or to the right, that is positive skew, in relation to the mean. Okay, in relation to the mean. Fine. Now, the skewness coefficient, like how you can find out about skewness. The skewness coefficient is given by mean minus mode. Okay, mean minus mode. So, in this case, suppose we'll see that, just remember this and we will talk about it in the next slide. There is something known as a skewness coefficient, and that is mean minus mode. Okay, fine. If it is positive, if your skewness coefficient is positive, it's a positive skewness. And else, if your skewness coefficient is negative, it's negative skewness. How to handle skewness? Like you can use log transformation, as I told you. If your value is pretty big, if you apply log transformation, there are many different transformations you can apply, log which has log terms. Okay. And we know that if there is a very big entry and you apply log to it, what it will happen? It will bring shrink it down to the smallest value. We saw that. Okay. Removing outliers, you can remove outliers also. Now, how to remove outliers? To remove outliers, you should know a technique how to identify outliers. In a small data set, you can see, just compare and find the most bigger one, largest one, and say this is an outlier. Now, outlier doesn't mean that it should be always the largest. It can be the smallest also. It can be like maybe a baby is coming to this class. A baby is sitting in this class, and we are trying to find the age of the students here. Then the baby will come under the range of 1 to 2. And your age is around 20 to 25 range. So that baby is coming in as an outlier. So that's a less range. And one 60-year-old person is coming here. That's also an outlier. Okay, so it can be both scenarios. The smallest one, the largest one also. You will learn in, I think, next semester about more about this regarding ML models, how decision trees are used to handle skewness. Okay, how decision trees can be used to handle skewness. Fine. So this is it is like when to use mean, when to use median, when to use mode. This is a normal distribution which is kind of symmetrical. You can see mostly you see this scenario here. The mean, median, and the mode are the same. So since it is symmetrical, the mean will be this one, and the mode means the most frequently occurring entry in your data is this one. Okay, because it has the highest amount of frequency counts. Highest amount of frequency counts. Okay, then what is the median? You can find that. Okay. So for this data set, you can easily see mean is equal to median equal to mode. Now let us come. Now let us come to the next case, that is skewed to the left. If it is skewed to the left, if it is skewed to the left, and you take the mean, what happens? If it is skewed to the left and you take the mean, then what will happen? a bigger entry, a bigger entry, a bigger entry will also affect your data set. A smallest entry will also affect your data set. A smallest entry will decrease your mean. A largest entry in your data set will increase your mean. Okay. So you can see this skew to the left means the smallest values are present here. And due to this smallest value, the mean which was here previously got shifted towards the left. Mean got shifted towards the left. Observe, mean got shifted towards the left. Okay, towards the left. I mean, you will see that the mean is shifting towards the side of skewness. Where the skewness is, the mean is shifting towards that side. Okay, so here the skewness is towards the left, so mean has gone to the left. Okay, fine. So mean you found out. Can you find out the mode? Can you find out the mode? Can you find Can you find out the mode? How can you find out the mode? Yes, the most frequency occurring element. So this is the mode. Now median should lie in between mean and mode. Okay, so it is lying here. So here what relation are you getting? If your data set is left skewed, what relation are you getting? See the picture and what relation are you getting? Mean less than median less than mode. Okay, if your data set is skewed to the left, now what is what is referred to as the coefficient of skewness? What is coefficient of skewness? Mean minus mode. Okay, so here the coefficient of skewness is mean minus. So mean is so what you will get, mean is less than mode. So this should be less than 0. So it is negative. So if it is negative, this is known as negative skewed. Okay. Okay till now. Now let us look into the skew to the right. Okay. Your data set is skewed to the right. Okay. What will happen? So you can see, I told you that what it tells you here, that it is skewed towards the right. So your mean will be pushed towards the right. Wherever the skewness is going, mean will be attracted towards that side. Okay, so your skewness is towards the right. So you can see the mean which was in the previous side, later in the previous slide, it is now appearing towards the right. So you can see the mean is here. Okay, mode of course is the maximum frequently occurring thing, occurring value, and median will lie in between them. So what is the relation here? Mode is it right? What are you telling? Tell mode greater than. I suggest you guys to revise this after you go home. Okay, we'll check. We'll check. I mean, fine. So I suggest you go and check this out. What do you mean by? You told this. It is fixed. No, you check it. You check it. No, it's a good thing. It's a good thing to get confused with. Hmm, hmm. Yeah. We'll check. We'll check. Hmm. No, this is how it will remember in your mind for a long time. It's more. It's wrong. Full. Ah. No, this will give as assignment. Okay. One of you will tell in next class. One of you will tell. Who will tell? How it? Okay. Fine. So you will see, irrespective of your answer, irrespective of our both answers, you gave an answer, I gave an answer, irrespective of both the answers, median is a quantity which doesn't change much. Median is a quantity which doesn't change much, is unaffected. Okay, unaffected what is going on. Okay, so what kind of central tendency measure should you choose if your data set is skewed? Yes, yes, because it is a quantity irrespective of the skewness, it is maintaining its relation. Okay, it's maintaining its what in any issues? So which measure to use when your data set is skewed? Median. Okay. So you see, I understand your confusion. I understand your confusion, which is greater. So I suggest you do some boggling after going the class. Okay. Anyway, so this is all about the skewness. Okay. Maybe we have something more, is it? We have something more. Okay. So what are outliers? Okay. So first of all, like outliers are values that are much smaller. It can be smaller quantity or it can be larger quantity also. So these are the values that are much smaller or larger than the rest of the data set. Okay. These are the values that are much smaller or larger than the rest of the data set. They can be caused by, you can see data entry mistakes, sensor faults. Okay. If the sensor went wrong and the sensor is determining the temperature, it might determine some faulty temperatures. Natural variation, this is rare, but maybe possible. And whether to keep them or remove them depends on the context we are working on. Okay. How to detect outliers actually? So one of the method is just by eyeballing them, eyeballing your data set is just sort your data set and look for the values that are far away from the rest. Look for the values that are far away from the rest. Okay. So in both cases, it is possible. If your value is very largest, then it will be in the much larger zone. If it is very small also, it will be towards the smallest zone. Okay. For example, you can see this is a tiny data set and almost it is sorted out. This is sorted data set. Okay. You can see it is sorted in ascending order, right? Is it sorted in ascending order? Yes. Okay. So you can see that what is the outlier in this case? Yes, because it's the biggest value here. Okay. Same, if this data set would have maybe minus 350, then this is also minus 350 is also a outlier. Okay. Fine. Now to detect outlier, there are two different methods or statistical measures. There are two different statistical measures, that is interquartile range and z-score. These two things we'll be seeing today. Okay. Now what is interquartile range? Okay. Interquartile range method, like first quartile, like Q1. Okay. It's the value at the 25th percentile. Okay. That means 25% of data is below this point. Q3, 75th percentile, 75% of data is below this point. Okay. Then the interquartile range is the difference between them. That is Q3 minus Q1. Okay. This tells us the spread in the middle 50% of the data. This tells us about the spread in the middle 50% of the data. Okay. So I suggest there is Q4 also. There is Q4 also. Okay. Is there Q4? What will happen if you take Q4? Yeah. So try to know more about this quartile. Okay. I think like most of the journals. So most of the journals, like we publish our works, the papers you will be studying for your capstone project are the journal articles, right? So those journal articles, what I suggest you, mostly it is from one journal, but different journals, journal is good, journal is bad also. Some journals are good, some journals are bad. So how to determine them? Therefore, they perform the ranking. Okay. The best journal means the top quality journals are Q1 journals. Okay, or Q1 journals. The middle quality journals are Q2 journals. The poor quality journals, like not poor, still okay quality journals are Q3, but below that any journal is not recommended, okay, to publish your work. Okay, so those may be predatory journals which take money for you to publish, which can publish anything. Okay, even if you write cat is red, they will publish it. Okay, so those kind of issues are there. So these usually apply in journals. You can see, so there are something known as Q1 journals, something like Q2 journals, Q3 journals. Okay, so this quartile they follow in journals, scientific journals. Okay, fine. Now how to determine outliers? Okay, so you calculate this, you calculate a lower limit and an upper limit. Okay, based on Q1 and interquartile range, Q3 minus Q1. Okay, so what you do, lower limit is given by Q1 minus 1.5 times the interquartile range. Okay, that is the lower limit, and the upper limit is given by Q3 plus 1.5 times the interquartile range. Now many of you might ask why you have chosen 1.5. That's the rule of thumb. That's the rule of thumb. I mean, it is a standard procedure to do it. Okay, so this is a rule of thumb, therefore we have chosen this 1.5. Okay, you can still go into details, into statistics why 1.5 is chosen. Okay, but you will see maybe 1.5 is an ideal candidate to do this, to detect this outlier. Okay, so what will happen, any value below the lower limit or any value above this lower limit will be an outlier. Okay, shall you calculate with an example data just to have a feel? Are you interested in doing that? Okay, so I'll give you a set of numbers in a data set, and your job is to identify the outlier just not by eyeballing, but by computing the lower limit and upper limit via interquartile range. Is that a good idea? So that you will know. Okay. Okay. Now, okay. Let us take this rainfall data. Okay. Just a set of numbers. Think of it like that. It is rainfall, monthly rainfall data in mm. So these are the set of numbers. Okay, I mean without looking also, I mean just by eyeballing the data you can easily predict what is an outlier here. Okay, but I suggest you that you try. It's a one time example you do. Okay, so another possible case or method is to identify outlier is Z score. Okay, so one method you learned is IQR, interquartile range. Another method is Z score. Okay, what is Z score? So it's a statistical measurement that describes how far a data point is from the mean. Okay, how far the data point is from the mean expressed in terms of standard deviations. Okay, so here in order to compute the Z score, you have to compute the mean and also the standard deviation. Okay, so to measure this, how you do this? So this is the Z score value of a data set, of a data entry point. Every point in your data set will have a Z score value. Mean is regarding a data set. Mean is regarding a data set, is it or not? Given a data set or a data column of numerical values, if you compute the mean, it will be a single value. Yes, you sum it up, divide by the number of data entry points, right? But the Z score is different. Z score is every entry point in your data in a column will have a Z score value. This is so you can see the difference between a Z score and a mean. Mean is for a particular column you will have a mean, that is a value, but in a particular numerical column every data entry point will have a Z score. Okay, so therefore that is defined as that entry point minus mu is the mean, this is the standard deviation. Okay, So you can see here what is x mu and sigma mean over here. Okay, x is the value of the data point. Mu is the mean of that particular data column you are looking at. Sigma is the standard deviation of the data. Fine. So this is how it looks like. This is a normal distribution, and you can see that mean lies exactly at the middle for the symmetry case. Okay. This is the first standard deviation, second standard deviation, third standard deviation, and symmetrically, this is the first standard deviation, second and third standard deviation. Okay, fine. So if you have a z score of 0, if you have a z score of 0, what does it mean? If your z is 0, what does it mean? It means x minus mu by sigma is 0. What does it mean? It means x equals to mu. It means x equals to mu. What does it mean? It is indirectly showing that the data point is exactly at the mean. Data point is exactly at the mean, which you can do the calculations also. Okay. If your z score is 0, that means your data point is exactly at the mean. So it is not further away from the mean. So therefore it is 0. A positive z score. What do you mean by a positive z score? If it is a positive, if your data point has a positive z score, it means it is above the mean. Therefore it is positive, because x minus mu will be positive if x is greater than mu. That implies z is greater than 0. Is it? Are you able to understand that? If x is greater than mu, then z is greater than 0. So if your data point is above mean, your z score is positive. Fine. Now let us look into what do you mean by a negative z score. Now you have a negative z score, it means data point is below the mean. So if x is less than mu, it implies z is less than 0. I mean, it is other way around also. Two ways. If x is less than mu, it implies z is less than 0. Z is less than 0 implies x is less than mu. Two-way road. It's a two-way road. One implies other, other implies the first one also. Okay, fine. So commonly data points with z score like greater than 3. Okay, this is a rule of thumb. I mean, you have to go deep into statistics to understand why this criteria is made, but this is just the criteria which I am just explaining here. I am just putting it down. If your z score is greater than 3 or your z score is less than minus 3, they are considered to be outliers. I hope you got that catch. Okay, the important point is if you compute the z score, if your z score is greater than 3 and your z score is less than minus 3, in these two cases, any data point which have z score in this range will be considered as an outlier. So therefore, you can see how to determine outlier based on interquartile range and also on the z score, right? Fine. So z score, like interquartile range, you determined a lower limit, upper limit. If your value lies on either of the cases, it is an outlier. Second case is based on the z score. If the z score value, if z score value z is less than 3 or I made a mistake. So z is less than minus 3 or z is greater than 3. These are the candidates for outlier. Okay, these are the candidates for an outlier. So what do they mean? They mean that the data points, they lie more than 3 times the standard deviations away from the mean. Okay. I hope that is okay. I mean, you don't have to, if you see the slide statements, it might be confusing. So you can play around with the formula. Okay. Suppose you got the z score to be 3.5. Let us say z score is 3.5. What does it mean? It means x minus mu by sigma is 3.5. What does it mean? What is x? X is equal to mu plus 3.5 sigma, isn't it? So what does it tell? It tells you that it is 3.5 times more, 3.5 times the standard deviation more spread out from the mean. You are adding mu plus something. So mu plus something means mu, then how much it is? It will be here somewhere, 3.5 sigma. I hope you can relate the wordings to the formula and to the visualization. Is it okay? Hmm. So this threshold you can actually adjust. So the Python code I will show you right now, Z score that greater than 3 did not work. It did not, it was not sufficient to get the outlier. In those cases, you can relax the tolerance a bit. That means Z greater than 3, you might drop it to 2.5. If you consider 2.5, you can get an outlier. You can relax this value. So 3 is not the 3. The 3 you are seeing, the 3 or minus 3 you are seeing right now is not the hard and fast constant to take care of. It can be adjusted based on your data set. Okay. So you can see, therefore, I've written the threshold can be adjusted. It can be adjusted based on the data set you have. Okay. So we will see a rainfall data and you will see that Kochi receives highest amount of rainfall. That's an outlier. How many are from Kochi? Kochi. Kochi, Kochi. Are you getting very like heavy rainfall there? No? Then the data set is wrong. Huh? Huh. Um, Maybe I can show you in next class. Okay. Maybe I can show you this in next class. I'm not getting it. I think it went somewhere or got deleted maybe. Uh, but there was a rainfall distribution here. Hmm. Anyway, we'll see this in next class. Okay. So I hope, so today what we discussed so far in the class? Yeah.